can you guess what is this? It is a transformer. Or can you guess what is installed on this pole? That is nothing but transformer. Or it is a transformer. You might have seen this type of device in the corner of your lane or at the end of your complex or at the end of any road. This type of the device you might have seen. It is nothing but a transformer. Electrical energy at power station produced at high voltages and transmitted through overhead lines to our homes, to our factories, to our schools and to our colleges. So we need to reduce this high voltage to the low voltage with the help of a transformer. So transformer is a device to decrease high voltage to low voltage, to change high voltage value to low voltage value. Similarly, a transformer can be used to change the low value to high value of the voltage. Thus, transformer can be utilized for the two purposes. What are the two purposes? One is to increase the value of voltage from low value to high value, or from high value voltage to the low value voltage. Thus, a transformer can be utilized to increase the value of the voltage or decrease the value of the voltage. In today's tutorial, I am going to talk about working, construction and mathematical expression of a transformer. The simplest type of the transformer is having the two windings. One winding is connected to the side of the supply, that is a supply side winding. Another one, a winding connected to the load side. Load means the bulb, tube light or any other equipment you are using for your purpose is nothing but called as a load. So there are the two windings. One is the supply side, another is the load side. The winding which is connected to the supply side is called primary winding, and the winding which is connected towards the load side is called secondary winding. Thus, the transformer having two types of the windings. One is the supply side, another is the load side. So, the winding connected towards the supply side is called primary winding, and another one which is connected towards the load side is called secondary winding. Today I have divided this topic into various parts. First I am going to talk about working principle, then construction, then current and voltage relationship, and at the end EMF equation. To understand the principle of working of transformer, first of all, let us consider a copper coil. The copper coil is made by using insulated copper wire. Now we will connect this copper coil with AC supply. As soon as we connect with AC supply, the AC current starts flowing through the coil. As the alternating current flows through the coil, a varying magnetic flux is produced around the coil. Now suppose we keep another coil near the first coil. We connect a bulb to the right side coil and the bulb gives light. That means bulb glows because the current starts flowing through the coil. Here the surprising action is that both the coils are not touching each other, even though the electrical energy is transferring from first coil to the second coil, from the left side coil to the right side coil. Here both the coils are electrically disconnected and magnetically connected. Now let us understand why the electrical energy is getting transferred from left side coil to the right side coil. Left side coil, we can call it as a primary coil, and the right side coil can be called as a secondary coil. Now when you start the AC supply, even though both the coils are not physically touching each other, the current is getting transferred from one coil to another coil. How it is happening and why it is happening, what we should do to make it more stronger, so that I am going to speak now. First of all, when the AC current is transferring from the coil, the AC current is a variable current. It is not a constant current. So when the current is changing, which is flowing through the coil is changing, and when the AC current is flowing through the coil and that is changing, that changing current will make the another effect in the coil. What is the another effect? When the AC current is flowing through the coil, a variable magnetic flux is produced in the coil. Now when the current flowing through the primary coil, EMF is changing in the primary coil. So the EMF is induced in the primary coil due to changes of current in the primary coil. So production of induced EMF in a coil due to changes of current in the same coil is called as a self-induction. That means in the primary coil, what is happening? What type of induction taking place? Self-induction taking place. Self-induction taking place. And because of this self-induction, there is a variable magnetic flux is produced, and this variable magnetic flux produced in the primary coil is linked with the secondary coil. So the flux produced in the primary coil is linked with the secondary coil, and this is not a constant flux, it is a variable flux. And according to the Faraday's laws of electromagnetic induction, whenever the variable flux is linked with the coil, then EMF is produced in the coil. That means in the right side coil, the EMF is produced because of the flux, variable flux of the primary coil. So EMF induced in the secondary coil due to flux changes in the primary coil. So EMF is produced in the secondary coil. The EMF is produced in the secondary coil will cause the electrical current to flow. The electrical current will flow through the secondary coil. Now, what do you call the EMF produced in the secondary coil? That is nothing but called mutual induction. It is a mutual induction. That means the electrical energy produced in the secondary coil because of presence of the primary coil. If you remove the primary coil, if you stop the electrical current AC supply in the primary coil, the EMF in the secondary coil will also stop. That means EMF in the secondary coil is not automatically produced. It is produced only when the primary coil is present and the AC current is also flowing to the primary coil. Then only the EMF will produce in the secondary coil. So induction produced in the secondary coil is nothing but mutual induction. Thus, electrical energy can be transferred from primary coil to secondary coil with the help of mutual induction. And this is a basic concept. This is the working principle of a transformer. Thus, transformer works on basis of Faraday's law of mutual induction. You see that we got the primary coil and the secondary coil, and when you switch on, then the flux is produced in the primary coil. So the flux produced in the primary coil linking with the secondary coil, but the all flux developed by the primary coil not linking with the secondary coil. What is the reason? The coil are not very close to each other, and lot of magnetic field which is produced by the primary coil that is linking with the secondary coil is also getting wasted. To overcome this problem, we can use a metallic strip, and on this metallic strip, if you do winding one over the another or winding side by side, so by doing that you can control the loss of magnetic flux developed by the primary coil, and maximum flux will link with the secondary coil. And but directly we cannot use a metallic strip. Reason is that if you use the metallic strip, you cannot control hysteresis losses, you cannot control the reluctance, and you cannot control the eddy current losses. You cannot control directly the heat produced in the transformer. So directly we do not use the total one piece of metal. We take the metal piece and we make small plates of metal piece and use in case of the transformer. Thus, a piece of metal is converted into a thin plates, and these thin plates are called laminations. These are all laminations. These laminations are developed from the big metal sheet. We do not use single metal piece. We convert them into sheets, and again the sheet given the special shapes called as the laminations. In case of transformer, there are the many types of the windings and various ways the winding is done. I am not going in the detail of how the winding is done. I am going to show you a simplest type of the winding here, so that you will get an idea how the primary winding and secondary windings are done in case of transformer. First of all, we have the lamination, and we do the primary winding, and we cover the primary winding by use of paper. These are the special paper. They are available in electrical shops. If you tell them electrical type of electrical paper, then they will provide you. And after this covering on the primary winding, we do the secondary winding, and again we do the paper covering, so that the primary coil and secondary coil do not touch each other physically. They should remain untouched. If they touch each other, then the short circuit may take place. Therefore, both primary and secondary coil should not touch each other. And after thorough covering, we tighten. We make both the coils quite tight, so that they do not move, not slide, not what is called remain loose. And after that, by proper lamination, we totally fix it. And from primary coil, we take out the 2 terminals for connection, and from the secondary coil also we take out the terminals. And there are as I already told you, on the type of winding and type of covering, we can divide the winding and transformer in various types that I am not going in detail now. So this is the way the winding is done, and 2 terminals are taken out for the primary, and 2 terminals are taken for the secondary for external connections. This is a practical transformer, and these are the laminations. All are lamination. They are insulated from each other. For insulation purpose, generally we apply the oxide film or the varnish, and here is the winding, and these are the 2 terminal taken out here, and here also terminal for external connection. And so the laminations are arranged such that they are very tight to each other. We can tighten them by using the nut and bolt system. here is the hole is done, and from here the one screw is drawn, and we tight the screw so that all lamination remain very tight to each other, so that the air gap should not present between the two laminations. And we don't use the single piece of metal, I told you already, to control the heat losses, hysteresis losses, and other kind of losses. We use the metal plates, and this all the metal plates are laminated with the help of varnish or oxide film. For the single phase transformer, there are the two windings, primary winding and secondary winding. Here we are talking about single phase transformer itself. Three phase transformer, here I am not talking about. And previously we have seen that primary coil and secondary coil, two inductive coils, and the electrical energy was transferred from primary coil to secondary coil with the help of mutual induction. Now here I would like to clarify that for simplicity I will call as a small size transformer and big size transformer, or low voltage transformer and high voltage transformers. What I do mean by low voltage transformer? Low voltage transformer are those which you are using in your small devices like mobile charger, or eliminators, or the music boxes, and printers, and stabilizers. There you are using small size transformers. And for the supply of electrical energy, for example to factory and to your house and your college, you are not using small size transformer, you are using big size transformers. For the small size transformers, we don't require oil tank, or we don't require any other special extra devices to be joined along with the transformer. Directly you just do the winding of primary and secondary and pack up it properly and directly use in your devices. That is in case of the small transformer. But when you talk about the big size transformer, you require special some other component along with it to supply the electrical energy. So here I'm going to talk about what are the extra components, extra parts required in case of the big transformers. First of all, let us have a look about constructional feature of single phase transformer. I am talking about the basic constructional feature of single phase transformer. First of all, we got a tank. Inside the tank, we place the assembly of primary and secondary winding along with the iron core. And this tank is attached with the cooling tubes both sides. Then there are the bushings for primary and secondary terminals. Primary and secondary terminals are connected to bushings, and so we call them as a bushing for primary terminals and bushing for secondary terminals. We got conservator. Conservator is connected to breather, and the tank is filled with the oil that we call as a tank oil, and the entire tank is connected to the explosion vent. So these are the basic constructional features. Now let us talk what are the various uses of these various constructional features of transformer. Terminal bushings. Bushings for primary and secondary windings are made from porcelain or ebonite and fitted to the tank at the top. Bushings are used for making connections with external wires. Transformer tank. Transformer tank is a fabricated metal sheet tank. The body of tank is either made from iron or steel. It is used to hold and protect the wounded iron core. It protects the coil assembly from outside environment. It provides extra space for expanding oil at increased temperature. The ends of tank provided with cooling tubes. Tank oil. Both inductive coils, primary and secondary coils, are placed in the oil tank. The oil used in tank are mineral oil, silicon-based oils, and bio-based oils. The main function of oil is used in transformer is to provide high thermal conductivity, must protect the transformer winding from electrical and mechanical stress. Cooling tubes. Heat produced inside the transformer due to so many reasons. Whenever the current passes through the coil, the heat is produced. We cannot control the 100% heat produced in the coil. So as the current passes, the coil becomes quite hot. And if you don't cool the coil, there are chances of damage in the coil. The coil will burn itself. So inside the transformer, when the coil becomes hot, that heat must be passed to the outside environment. For that purpose, we use the oil inside the tank. And at the end of the tank, cooling tubes are provided. So heat produced in the tank is to be passed to the outside with the help of cooling tubes. And cooling tubes are provided at the end of the tank. You see, when we are using a transformer and there are the coils and current is flowing through the coil, and we know that whenever the current flows through any metal, the metal becomes hot. Therefore, the coil also becomes hot when the current is passing through the coils. When the coil becomes hot, the oil inside the transformer also becomes hot. And when this oil becomes hot, after the certain limits, certain temperature, the oil quality changes. There are the chances that the oil is becoming more hot and the various gases are produced. And when the many gases are produced, these gases should not accumulate inside the tank. And to remove these gases and from the transformer, these gases must pass to the outside world, outside environment. For that, we got a relay called as a Buchholz relay. So Buchholz relay is used to protect the transformer assembly in case of dielectric failures. And this Buchholz relay is connected between the oil tank and the conservator. Conservator is little higher compared to the height of the tank, so that the accumulated gases must easily expel to the environment. When the Buchholz relay operate, then a whistle or alarm will be given automatically, so that the operator will come to know there is a certain fault has taken place. And whenever the Buchholz relay operate, the circuit breaker will also operate and will shut down the entire system, so that you can protect the transformer from the damage. Whenever the oil in tank becomes hot, oil expands and air at the top of the oil is expelled out of the tank. When the transformer cools down, the oil contracts and cool air again enter the transformer assembly. This process, hot air going outside and cool air coming inside the transformer, is nothing but called as a breathing of the transformer. So the air which is entering the transformer should not contain the moisture. The job of the conservator is to remove the moisture from incoming air. Explosion vent. Explosion vent is fitted at the top of tank. It has diaphragm made out of glass sheet or aluminum foil or bakelite sheet. If pressure increases due to gases beyond a limit, then this diaphragm bursts and releases the pressure inside the tank and avoid damage to the transformer. You see, till now what we have learned? We have learned that AC current passes through the primary coil and a variable magnetic flux. Variable magnetic flux is produced in the primary coil. And this variable magnetic flux produced in the primary coil not only links with the primary coil but also links with the secondary coil. So the variable flux also linked with the secondary coil. The variable flux linked with the primary coil produces EMF in the primary coil. So, and the variable flux linking with the secondary coil also producing EMF in the secondary coil. That means EMF is produced in the primary coil as well as the secondary coil. And the flux passes through this iron core also. That means iron core is strengthening the flux produced by the primary coil. Now, the EMF produced in the secondary coil will depend upon how many turns are there. You see that when you are doing the winding, you are counting how many turns. 2 turns, 3 turns, 4 turns, 100 turns, 2000 turns, 1000 turns, 500 turns. So whenever we do the winding, we count the winding with the number of turns. The number of turns can be easily counted with the winding machine. A digital counter is there on the winding machine. When you are doing the winding, the machine automatically counts how many turns you are winding. So here we are doing the winding of the primary and counting the number of turns of the primary and counting the number of secondary as well as. So when the AC current is passing through the primary coil and the flux linkages with the secondary coil, the EMF is produced in both primary as well as the secondary coil. So we want to find one equation, how much EMF produced in the primary coil, and we want to find one equation, how much EMF produced in the secondary coil. So let us say E1 is the EMF produced in the primary coil and E2 equals to EMF produced in the secondary coil. Now we have to find EMF equation of transformer. For that purpose, let number of turns of primary NP and number of turns of secondary NS. NP equals to number of primary turns, and NS equals to number of secondary turns. And AC supply, this is the AC supply, this is a symbol of AC supply, and it is a flux. Flux is denoted by phi. Now let us say the maximum flux, because the total flux is always not linking, a little bit there is a wastage of flux. So how much flux maximum linking with the iron core is called as a maximum flux. Maximum flux in iron core. Now, this is a symbol of AC supply. This is called waveform. It has a positive half cycle, negative half cycle. This is alternating waveform. Alternating, it is a waveform of EMF or it is a waveform of current. It is called as a sinusoidal waveform, sinusoidal wave, and it has a positive half cycle and negative half cycle. Phi m is a flux, maximum flux in the iron core, and that is also equals to maximum flux linking with either primary or secondary winding. Now, when we have the alternating supply, it is a positive half cycle, negative half cycle. The negative half cycle and positive half cycle together called one cycle. And time taken to complete one cycle is nothing but called time period. Time period is measured in seconds. And we can draw the graph for flux, or we can draw the graph of current, or we can draw the same graph can be drawn for the EMF developed in the winding. Here I have shown you sinusoidal wave in slow motion. It becomes maximum and reverses the direction. It takes some time to become maximum and takes some more time to become minimum. The alternating cycle become positive and negative, and in every half cycle they increase and decrease. They do not decrease suddenly, they take some time to become maximum and minimum. Suppose this is sinusoidal wave and the total time taken equals to t, and time taken for one cycle is nothing but time period. Now we divide the given waveform into four parts. This is the first part, this is second part, and this is third part, and it is fourth part. Now total time for four parts is equals to capital T. For four parts, the total time consumed is equal to capital T seconds. Therefore, for time consumed for one part equals to 1/4 of T seconds. Since time period equals to 1/frequency, that is T equals to 1/f dividing both sides by 4. Therefore, in 1/4 of time period, the frequency is nothing but 1 upon 4f. Let us call it as a equation 1. Therefore, this is the maximum flux. Therefore, the flux becomes maximum in 1/4 of time period. Now next step, to find average rate of change of flux. Now we'll find out average rate of change of flux. Average rate of change of flux equals to maximum flux linked either with primary or secondary coil upon time taken, that is equals to maximum flux and time taken equals to T upon 4, and the flux is measured in Webers and time in seconds, therefore Weber per second. But T upon 4 equals to 1 upon 4f, that is equals to average rate of change of flux equals to 4f multiplied by 5m, that is equal to 4f 5m. Let us call it as a equation number 2. Now we know that average induced EMF per turn equals to average rate of change of flux. This is EMF induced per turn. So this is according to Faraday law of electromagnetic induction. Average induced EMF is equals to average rate of change of flux. I repeat once again, average induced EMF per turn is equals to average rate of change of flux. So average rate of change of flux per turn is nothing but 4f 5m, and the EMF is measured in terms of volt, therefore it is volt. Therefore induced EMF per turn is nothing but 4f 5m volt. Value of induced EMF. RMS value of induced EMF equals to what? RMS value of induced EMF equals to form factor of sine wave multiplied by average induced EMF per turn. So form factor for the sine wave is nothing but 1.11, and average value of induced EMF is nothing but 4f 5m. So that is equals to 4 into 1.11 F into phi m. Therefore, RMS value for induced EMF per turn equals to 4.44 F into phi m. Now we are having primary winding, we are having secondary winding. EMF induced in the primary winding is EP and EMF induced in the secondary winding is ES. Number of turns in the primary winding NP, number of turns in the secondary is NS. Some people call N1 and N2 also. In place of NP, they call it as a N1, and in place of NS, they call it as a N2. So, but we already labeled it as a NP and NS. Now, RMS value of induced EMF in primary winding equals to induced EMF in primary per turn into number of primary turns implies EP equals to 4.44 F phi m multiplied by number of primary turns, that is NP. Therefore, EP equals to 4.44 F phi m into NP. That is, EP equals to 4.44 F phi m NP, and in the unit is a volts. Similarly, EMF induced in the secondary winding ES equals to 4.44 F phi m into number of secondary turns. How many secondary turns? They are NS, and the unit would be volts. Therefore, EMF equation for primary winding EP equals to 4.44 F phi m NP volts, and for the secondary ES is equal to 4.44 F phi m NS volts. So in today's video we learnt about principle of working, construction and EMF equation of transformer. How do you find my presentation? Please give me your feedback. And I request you one more thing. At the end of this video, we have done EMF equation. So you go through once again and write the entire equation on a plain paper, step by step, for better and perfect understanding. Now I will come with another video shortly. You suggest the topics you wish to see on my channel. Come with another video very soon. Till then, wish you good luck. All the best.